So, moral of the story is I'm currently, I don't want to say poor, but currently poor. So I was gonna go buy us some M&Ms, but poor. So what I'm gonna do is buy Halloween candy after Halloween, so then it'll be discounted. So yeah, I know. Halloween candy after Halloween. So we'll do this probably again. But what is your favorite color of M&M? Yeah? Do they taste different? They're not all the same. So they came out back in the day, they came out with like an all green packet. It totally tasted different. Just FYI, in case you're wondering. You're calling me mental? Yes. Oh, well, awkward. Okay, so the company that makes milk chocolate M&Ms claims the following distribution: the 13, 14, 20, 16, 24, and 13. So you have majority blue and orange. I feel like that's not true, but that's just me. So we're going to take a class sample and record the results. Okay. Again, respectfully, since I don't trust you anymore with samples. That's not disrespectful. Let's say we had 55 brown. Let's say we had 92 yellow. No, we would like run this a lot. All right, we'd have 101 orange. Let's say we have 73 green, 74 blue, and 66 red. So how many total M&Ms do we got? Going home. I quit. That's going to be 461 when you add it all together. All right. Remember, that's your sample size, right? Everybody good? David, are you okay? Okay. All right. So now let's go ahead and state our like null hypothesis. Okay. Our null is that the company said, hey, we have 13% are brown. We have 14% are yellow. We have 16% is green. 24% is blue. And 13% are red. The original? It's the claim that is being made. All right, so the null hypothesis is the claim distribution of color of M&Ms is true. That's the null hypothesis. The alternative is that the claim distribution of color M&Ms is not true. Rebecca! Okay, so what would make the null, like what would make the alternative? So it means that two of these proportions would be incorrect, right? Okay, because you can't just have one be incorrect. One would impact another one. Does that make sense? Like if I change 13%, then it's going to impact something else. David, are you okay? Okay, so at least two of these proportions are incorrect. At least. So if I had that 13%, if it was instead 16%, well, one of these proportions would change. Everybody else gotta ask it again. A s'more is a link. It's actually like a website. What'd you say, David? PI? one of the PIs are incorrect. So that means that any single one of those could be incorrect. Andy, what was your question? If at least two of the PI are incorrect. Yes. Incorrect. We're doing great. All right. Let's suppose that the M&M's claim distribution is correct. If they are correct, how many of each color would we expect to get in our sample? So if this claim is correct, those distributions that we listed up at the top is correct, then we're going to take each of those proportions and multiply it by 461. So we're going to say 461 times 0.13 times 0.14 times point. I can remember this one. You're not going to round it all. So brown would be 59.93. Yellow would be 64.54. 92 would be, I'm sorry, orange would be 92.2. Green would be 73.76. Blue would be 110.64. And red would be 59.93. Way we get this is we take our sample and we multiply by our proportion. That would be our expected counts. Expected counts. Go ahead. Because when we multiplied our sample times our proportion, that's the number we got. Okay, so if we added all of this up, it would give us exactly 461, correct? If we rounded up, it would no longer give us 461. It would be over the proportion. This is just what would be expected if the proportions are true. This is expected. This is not what was observed.
Yeah, so that's around it because it's not like true to reality. It's just like the meaning of all.
Because like you can't have half an M&M, right? But you can have a mean or an average of 4.62, right? Okay, so we're going to put in our observed counts and then our expected count in these columns. So we're taking what we got in number 1 and what we got in number 3, and we're just putting them in a column, making them super organized. So 55, 92, 101, 73, 74, and 66. That was what we observed. That was the sample that you didn't do, but you did do. Okay? The expected is what we just calculated. So expected is, yes, Mo. So we took our proportions that we have in our claim and we multiply it by our sample size, which was 461 from number 1. That's all we did.
What does that mean?
It's just our expected. So like if we say, hey, there's 13% that are brown. Of the 461, how many would we have then? Yes, no? Okay. All right, we're putting in our cute little chart. That's all we're doing. We're just copying down. Good? Okay, now let's do something crazy. Subtraction, yay! Yay! So observed, so what you got in this column, minus your expected. So observed minus your expected, that's going to give me negative 4.93. And then let's say that we take this and we square it. That's going to be 24.30. And then if we take that and we divide it by our expected, then we're going to get 0.405. Yes, Jasmine just said it. This is the chi-squared formula.
Maybe let's do this in biology.
Yeah, you've seen this kind of before in a couple classes, actually. All right, so go ahead and fill in the rest of the table. Take a second, you're filling in the rest of the table. Any math words ever. Ever. 27.46, 8.8. I'm just gonna help you. Negative 0.76, negative 36.64, and 6.07. 754.05, 77.44, 0.58, 1,342.49. That's crazy. And then 36.84. All right, catch up first. I did. That was pretty funny. Did you just say coffee is boring?
Huh?
Did you say coffee is boring?
Coughing is boring.
Oh. Okay.
Yeah.
All right. If you divide it by the expected value on this last column, oh, whoa. Yeah, I'm not a fan. A long table. Okay. No, it's chi squared. Chi squared, not chi squared. Failure. Okay, when you added up all the numbers in the last column, what'd you get? 25.685. You didn't get that one? Oh, what? Oh.
We already know. What is that?
Okay. So you told me that we get 25.685. Okay. So how we did that is we say the chi squared is equal to the summation of the observed minus the expected squared divided by, yep, the expected. You do this already, like in most of your science classes, you do this.
Are you sure?
Yes, I'm very positive. Chem major and previous bio major. Yes, you've done this before. I was. Because I could go to sleep and be a math major.
Did you major in anything else besides math?
So I have an applied mathematics and psychology degrees. I've got a master's in sports management, and I'm going back for a master's in education. So, yeah. No.
College students?
No. Because I would fail all of them and then get in trouble.
No.
Because like in college, what? Dr. Coach, Mrs. What? Insane. I want like a t-shirt with all of that on. No. I should never tell you all that. Anytime. All right. So here is the p-value. So I'm going to show you how to put this in the calculator a little bit later, but I'm going to show you what it looks like typing it in. So first of all, I'll give you the keystrokes in just a second. So this is going to be chi squared CDF. Okay. This is your p-value. This is how you're going to find it. You're going to do what you just found. So what the chi squared is. So 25.8.685. And then the upper limit is going to be 9,999. No.
Okay.
Okay. Your degree of freedom. Let's have that conversation. I always thought this was dumb, but it's okay. The degrees of freedom is n minus, I'm sorry. It's how many things you have minus 1. So things you have minus 1. So how many colors do we have in a pack of M&Ms?
Six.
We have 6. So 6 minus 1 is, okay, so our degrees of freedom is 5. Okay, so that's going to be my last thing. And so that's going to give us a p-value of 0.0001. So this is your lower limit, this is your upper limit, and this is your degrees of freedom.
What is your degree of, like, what is it when you look to?
It's how many options you have minus 1.
What, like movies?
So it helps you with your chi-squared. It's like showing you the number of categories, accounting for one of them is probably going to be wrong. Again, dumb. I think it's dumb, but that's just me. All right. So on number 5, it says, what value would we get for the test statistic if our sample was very close to what was expected? What value will we get for the test statistic if our sample was very close to what is expected?
1.
Mm.
Less than.
So it would be close to 0. So if what is expected, come in. So, hey friends. Yay. Thank you so much. All right, so if we got what was expected the same to be as what was observed, it would be close to 0 because observed minus expected would be, values would all be small. This is a multiple choice question on your AP exam. What value would we get for the test statistic if our sample was very far from what is expected? So it would be a large number because the observed minus expected values would be large.
Large number of expected consequences.
It would be a large number, comma, because your observed minus your expected would be larger. All right, flip the page. Okay, so what we talked about was we talked about the hypothesis. Hypotheses. So we got chi-squared test of goodness of fit. Goth. So chi-squared goodness of fit. We talked about the HO, which is the claimed distribution of categorical goodness of fit. Categorical variable is true. The alternative is that the claim distribution of categorical variable is not true. Categorical variable is going to depend on your context. So like, what are you actually talking about? What? We can't make the claim that it's false. We're proving that it's not true.
That's not true.
So if you're not telling the truth, are you a liar?
Yeah. Yes. It was. That's what
So does that make you a liar? So everything that comes out of your mouth is a lie. So then you're not telling the truth. You're not a liar though.
You're not. What's on the paper isn't true.
Something
Then
is
it can't
affecting
be
the data.
not false because it's false. Like it's not true. It's false. It's literally no. It's not.
So is every sample going to follow what is going to be expected? Like,
No sample that like nothing is necessarily a problem with it, but it's not true to the actual reality. What we're finding, it's not true, but it's not false.
because we can't say, hey, you're going to always follow this like parameter. Like, hey, it has to always fall inside of this interval. Well, sometimes occasionally it's going to fall outside of it. So we can't make the claim that it's always going to be true or it's going to be false, right? So we're going to say, right. But is it always going to happen that way? Is it going to be false always?
It's also, that's when we have like type one descriptive error, where those who are doing something to be like untrue and stuff, it doesn't mean that reality matches what we've got.
Okay, so then easily, how can we say that it's true?
Remember, statistics don't want to say, hey, this is going to happen 100% of the time. They say approximately. They use all those ly words so that they have some level of covering their butt.
Like we're supposed to act like it's likely or stuff like that.
Like, why would you say that it's true?
Because it's either true or not true. It can be false and not false. It's not going to be true and false.
Not always true.
David, oh my gosh, not true. Just use the lingo. Just use the lingo. I know, it's frustrating. I think it's stupid too, which is why statistics is not my favorite. It's silly. All right, so we talked about the chi-squared. So we said the summation of the observed minus the expected squared divided by the expected. We said that the expected is found by taking n times p. We talked about the degrees of freedom, number of categories minus 1. And if we talk about the distribution, we talk about the distribution. So janky curve. Okay. The p-value falls in here. And the way we found the p-value is we did chi-squared CDF. We did our lower, which was the chi-squared. Our upper is going to be 9,999. And then you're going to state your degree of freedom. Okay, go ahead and do A, B, and C. Yeah, go ahead and do A, B, and C and D, and I'll help you on E. Yep, you can do A, B, C, D. All right, so once you get to part C, you can actually type all this stuff in and it'll do it for you. So if you go into your calculator and you type in the observed list, so that's yeah, the list that they give up at the top, right? You type it in the table. Yeah. So you make a list of the observed, you make a list of the expected. So you're gonna have 2 separate columns. Make sure that you title them up at the top. Okay. Then you can hit menu, statistics, stats, chi-squared, GOF, and then type in the list of the observed, like the name, the expected, and the degrees of freedom, it'll actually draw the graph for you, tell you the p-value, and tell you the chi-square. Okay, so I would try this in your calculator. Okay, the chart that they give you is the observed. The expected is what you have to find, and then you can do all of this. Yes, so take a second, like try it, because it's going to take a little bit of practice. Okay. I paused the music the other day, and somebody was singing. It was awesome. All right, so state the appropriate hypothesis. So what is our HO? What's our null? Okay, so if we summarize that in one sentence. Okay, so they're equally likely, right? Okay, so our null is that births. One moment. Let's try this again. The null is that the births are equally likely. Wow. Across the days of the week. Okay, what's the alternative? The births are not equally likely across the days of the week. Okay. All right, when you calculate the expected count for each day, what would that be? Births not equally likely across days. It's this word. Y'all never seen that before? Okay, my 7th grade teacher used to use the quotations all the time, just to make it easier to write. If you want to write the words out, that's fine. So really quick, when we find the expected count for each day, what's the likelihood of it being on a Monday? What's the probability of a birth happening on a Monday?
1/7.
1 out of 7. So we're going to take 150, because that's the total number of births, and multiply by 1/7, right? And that's going to be our expected value for all of the days. Y'all seem shocked. 21.47, right? Or 21.4, JK, 21.4, right? So again, when we calculate the expected count, and I think it throws it off when it says for each day, as if it was like something different each time. Expected is going to be N times P. So we have 150 births, and we're multiplying it by 1/7. And that gives us 21.4. Now you've got to calculate the value of the chi-square test statistic. So we're going to say chi-square is equal to, we're going to take each value, subtract the 21.4, square it, and divide by 21.4. We're going to add that to the next day. And we're going to add that to the next day, and the next day, and the next day, and the next day. What's up, babe? Why is it what? Yes. What's the probability of getting each day of the week? Because what is our null hypothesis? That each day is equally likely. So when you do that, you're going to get 13.6. Now, if you did this with your calculator, that's fine for a multiple choice question. If it's an FRQ, you're having to show this work. Does that make sense? I don't want you to die. Yes.
That like typing it out on a calculator as the individual stuff or put it.
So what we're doing here is what would be like your FRQ. You would have to show the chi-squared, the degrees of freedom, all of that going down. Just putting, like showing what you put in the calculator isn't enough. You have to show why it doesn't work. Okay. How many degrees of freedom is there? Because we have 7 days minus 1, that's 6. So it's how many categories? Oh, okay. I like this definition of degree of freedom. Each number of independently variable factors affecting the range of states in which a system may exist. Maximum number of logically independent values as degrees of freedom. Okay. All right. So now what I want you to do is I want you to find your p-value. So if you went in and did the goodness of fit and followed those calculator instructions, you would have got chi-square CDF. The lower is 13.6. The upper was 9,999. Degrees of freedom is 6. That should have gotten you a p-value of 0.034. So are we going to reject or fail to reject the null? He's less than 0.05, so we did that. 0.034 is less than 0.05, so we reject the null.
But no, that's not for this stuff.
So remember the whole your alpha is normally 0.05 unless stated otherwise. Boom, 0.05. So on that one, flip the page backwards. The question was asking if the observed and the expected, if the test statistic in our sample was close to what is expected. So there's not much of a difference between observed and expected. Yep. Yes. So do we have convincing evidence or do we not have convincing evidence? We do have convincing evidence that births are not equally likely. Nobody gets born on a Sunday? Are you really? Hey, I don't know. Sunday? I was on a Wednesday. Yeah. I was brought home on Thanksgiving. I had a fever when I was born. Yeah. Turkey baby, for sure. Huh? Exactly. Well, I was. Yes. What is your favorite color of M&M's? Part 2. So record the information from the previous lesson. So you're observed and then you're expected. So that little chart that we did on the last one, that's what we're putting back here. All right. Ooh. Okay. So all I'm doing is copying down the information that we had on the last one. Nothing new. Right. Y'all should be writing. Oh, on y'all's FRQs, you keep forgetting the 4 C's. And the 4 C's are choose, check, not chooses, choose, check, calculate, and then conclude. The biggest problem that y'all made was y'all didn't do choose, and most of you didn't do conclude. So automatically you were starting at a 50. That's if you got these parts right. Okay. Most of y'all got the check because you got the 3 little things. Most of you got the calculate. I gave you like majority of the points if you got like the formula and most of the numbers right. But the choose part is where y'all messed up. You have to state what procedure you're using because we're getting more and more different types of tests that we're going to use. Okay. You also didn't state the parameter. You didn't even say what you were talking about. Okay. You have to clearly define it. You act as though the AP examiner is, or the reader is dumb. They don't know what you're talking about. Right? Yes, no, maybe. Okay. Quit messing this up. This is the give me points. Okay. Conclusion, if like you don't know these first 3, then you can't do the conclusion. Conclusion is some sentence that you probably had to memorize and you just plug in context. Okay. Good Lord. Okay. So we're going to choose the procedure. So the one that we've been talking about is the chi-squared test for goodness of fit. Okay. Our significance level, we haven't stated otherwise, so our alpha is going to be 0.05. Looks like a little fish. Okay. So let's go ahead and talk about the hypothesis. Hypothesis is the claim distribution, the same as last time, of color M&Ms is true. The alternative is that the claim distribution of color of M&Ms is not true. Now, on this one, we don't have to state the parameter. On this one, we don't have to do a statistic. On this one, we don't have to have evidence for alternative. Okay. You're going to check your conditions. So the parameter, there's no like P is equal to this, right? So we don't have to state what P is. The statistic, we're not looking at we're looking at one specific thing, but we don't have to state this. And then the evidence for alternative, we're trying to find that out if there is evidence for it. Okay. All right. So check the appropriate conditions. Go ahead and find random sample, 10% and large counts. Go ahead and take a moment. Try that.
And we think the parameter is the true proportion of colored M&Ms from the organ.
We're gonna talk about that in a second. You don't have to do parameter and statistic on this one. You just have to state what procedure and what are the hypotheses. Yep. Yes, random sample. All right, let's look at our checkyard conditions. Ready? So for random, did we take a random sample? What? So 461 M&Ms. So this means that we can generalize to the population, right? Generalize to the population. Fabulous. What about 10% condition? Is 461 less than or equal to 10% of all M&Ms ever in the world? I think so. Okay. So sampling without replacement is okay. Okay, large counts, all expected values, are they greater than 5? Notice how this number changed. Yeah. So are all your expected greater than 5? Yes. Here's the new part. Sampling, I'm gonna do a different color. Sampling distribution is approximately chi-squared. New thing. Okay. If you looked at the curve from the last part, it wasn't a normal curve. It was kind of skewed right just a little. Yeah? Okay. For calculate, there is no general formula. There is only the specific formula, which is your observed minus your expected divided by your expected squared with the summation of that. So with the general formula on the last one was like point estimate plus or minus the margin of error. Then it had like actual specific like variables that you plugged into, right? With this one, it's literally what you observed minus what you expected divided by what you expected. There's no variables for that. That is the formula. Yeah. Okay. Now we're going to plug in the numbers. So we're going to take each one of our observed minus our expected and do the whole process. Again, if this is an FRQ, you're going to want to show all your work. If it's an MCQ, just use your calculator. Okay, so we're going to plug them in. So chi-squared is equal to 55 minus 59.93 divided by 59.93. We're going to add that to 92 minus 64.54 divided by 64.54. And then we're squaring the top. And then we're going to add that to all the other numbers plus 66 minus 59.93 divided by 59.93, squaring that one. And when we do all of that, we're going to simplify each fraction, which is going to give us 0.4 plus 11.68 plus 0.84 plus 0.01 plus 12.13 plus 0.62, which gave us a whopping total of 25.68. That is what we found in the last one. Okay. When you plug this all into your calculator, you got this lovely graph of like a slightly right skewed graph. And that's 25.68 for the chi-squared, starting from 0. Our chi-squared degrees of freedom, that was 5, because there was 6 M&Ms minus 1.
Question. Okay. So the reason why, like, the checker can just send them to practice because checker is going to use key values in the equation. Like, the first, we are using specifically the chi-square. That's all. Just we're saying what value we need to get, we probably test with this, so not sure key value. That was the very suitable.
On the front page, okay, we found the p-value, we never made a conclusion. Okay, on the back page, we made a conclusion with the p-value.
But you're using two different, like, you're using excitement, like, the first page was about like, the high-school number.
Right,
Which is gonna extend it using p-value itself.
right. Okay. Okay, you're good. No worries. So now, when you plug this into your calculator, your p-value is going to be 0.0001, and your test statistic is going to be your chi-squared. Everybody good? Okay, nothing new. We just literally summarized what we just did, just in an FRQ way. Okay, now we're going to actually make the conclusion. So, assuming that your null is true, assuming null is true, which is the claim distribution of color is true, there is a 0.0001 probability of getting a chi-squared value of 25.68 or greater purely by chance. So now we've got to say whether we reject and do we have convincing evidence. So 0.0001, is that less than or greater than 0.05? Less than. So are we going to reject or fail to reject? We're going to reject. And do we have convincing evidence? Yes. Okay, it's the same process as what we did last time. The difference is finding the test statistic. We have convincing evidence that the claim distribution of color for M&Ms is not true. Okay, I'm gonna erase that and write the rest. So because 0.0001 is less than 0.05, we reject the null, and we do have convincing evidence that claimed distribution of color for M&Ms is not true. Which that's true. Like if you go open a bag of M&Ms, you're gonna open it and you're not gonna get majority what? Orange? Yeah, that's not gonna happen, right? Each bag is going to be completely different. Here's the new part. The largest component of chi-squared is 12.13. If you look back up where you plugged in those numbers, 12.13 is what you added into that chi-squared. Okay? And that's because the observed of blue is much lower than expected. Okay, so with chi-squared, you're still saying the probability of it happening, you're rejecting or failing to reject, and do you have convincing evidence? And then now you're going to talk about, well, what was the most impactful part of the chi-squared test? Okay. So it is the same 4 C's as the last unit. Same thing, different formula, add on what is the biggest component. All right, go ahead and flip the page. Okay, summarizing. Whoop-oo. Yay. So we still got the 4 C's. So we're still gonna like choose, check, calc, and conclude. For the love of all things good and holy, quit forgetting to choose. That's a fourth of the points. Okay. So chi-squared goodness of fit. You're gonna have no parameter and no statistic. You're still gonna check your random 10%, and then large counts is your expected has to be greater than 5. What's up, friend? For calculate, oh my gosh. Calculate, you're gonna have observed minus the expected squared divided by the expected. You have to show the components. So where we literally added up each individual fraction, that's what you have to show. And then conclude, you're going to interpret P. You're going to decide and conclude. Conclusion, bless. And then you're doing your follow-up. Okay, which is what we said at the very, very end. The largest component, blah, 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 blah. So for your follow-up, you're going to say the largest component of chi-squared is whatever number, because the observed was of whatever it's observed was higher or lower than expected. Start on the next part. A traffic light is set up to provide red light 80% of the time. That's yellow for 5% of the time and green 15% of the time. Local resident is suspicious that the light is not functioning according to the claimed distribution. He sets up a trail camera, programs it to take a picture of the light at 200 randomly selected times throughout the day. Here's the result: 173, 13, and 14. Is there convincing statistical evidence that the light is not functioning according to the claimed distribution? So first thing you gotta do, you gotta choose. Choose. So what kind of test are we doing? Chi-squared, not chai. That's a latte. Oh my God. Okay. The goodness of fit. What is the null hypothesis? Okay, so the claim distribution of the frequency is true. You can also say, hey, red is 80%. You can say yellow is 5. Or, yeah, 0.05. And then green is 0.15. Okay, what's our alpha? 0.01. And then what's our alternative? Claimed is not true. Okay. Now we're going to check. Is it random? It said 200 randomly selected picks, right? Is it the 10% rule? Is 200 less than or equal to the 10% of all possible light times? Okay. And then large count. So all expected counts, is that greater than 5? So sampling distribution is approximately, so we say chi-squared, chi-squared, chi-squared. So it's not normal. Yeah. Okay, calculate. So you're now going to actually hand calculate all this junk. Good morning, sunshine. Okay, so you're going to first write out the formula for chi-squared. Then you're going to plug in each observed and then each expected. Okay. So for calculate, give me 2 seconds. And you can check this with your calculator. Okay, so just because you're doing it by hand doesn't mean that you can't just like plug it in and check. Okay. All right, so we're on calculate now. So we've got chi-squared is equal to the summation of observed minus expected squared divided by expected. You actually did this in algebra, you just don't remember it. So that's going to equal 173 minus 160 divided by 160. And we're squaring that. And we're going to add that to 13 minus 10 squared divided by 10. And 14 minus 30 squared divided by 30. Let's hope that your AP exam, if you get this for an FRQ, that you only have like a couple of data points. You don't have like 15. Okay, still have to show these fractions. So we're going to simplify these fractions, and that's going to be 1.06 plus 0.90 plus 8.53. That's going to add up to equal 10.49. This guy's your biggest component to keep in mind for your conclusion. We always got to draw a picture of our lovely graph. So again, slightly right skewed. Here is that chi-squared. So we got 10, 10.49. What's our chi-squared degrees of freedom? Right, because we have 3 options minus 1. 2. And our p-value is going to be 0.0053. There it is. What I'm about to say. Okay, so there is a table on your orange formula sheet. Okay, on the very back, there's the chi-squared table. Okay, so you've got your degrees of freedom going along the side, and then you have your tail probability. We're going to talk about how to read this later. I would prefer you using your calculator because that's going to be faster. Okay. All right, now we're going to actually conclude. Okay, so with your conclusion, we're going to assume the null is true. There is a 0.0053 probability of getting a chi-square value of 10.49 or greater purely by chance. Okay, so we're going to conclude. Assume null is true. Okay, and you want to kind of state in context the null. So we're going to say red is 80%, yellow is 5%, and green is 15%. There is a 0.0053 probability of getting a chi-squared of 10.49 or greater purely by chance, bless. And because where's your p-value? 0.0053 is it less than 0.01? Do we reject or do we fail to reject? We reject the null. And do we have convincing evidence or do we not? And we do have convincing evidence for what? So the light is not working properly. Okay, again, that's a review from last unit. Then the next thing is the follow-up. The largest component is what? So the largest component of your chi-squared is 8.53, because observed green, was it lower or higher? Was lower than expected. That conclusion's a little long. All right. So will you get accepted to college? So for many of the major universities, applicants are either accepted, denied, or waitlisted. By the way, those are different. Waitlisted means they like you, but just not right now. Denied means they don't want you. Does that make sense? Okay. A random sample of 200 applicants from the University of Michigan and a separate random sample of 150 applicants from Ohio State, boo, were selected and their admission decision was recorded. So the table shows the results. You got to find the total. So add up the rows and the columns. Add up the rows and the columns. Rows and the columns. I got 350 in total. So how many samples were selected? How many places did we go to? Two samples. And what were they pulled from for the populations? So one was all applicants at the U of Michigan, and two was all applicants of the terrible school of Ohio State. I've got one kid in my second block that just talks about Ohio State. And I'm like, you're not even from there. Like you don't have any family. There's no correlation, no connection. You don't even go here. Huh?
You seen her?
Yeah, he is a senior.
You don't go there. You don't go. I'm smelling you.
You what?
You don't go there. You don't go here. Just like smelling you.
Exactly. Failure. Yeah, but boo. Because they have one good year every 30.
That year's still really good.
They're like, yes. I'm like, nobody has heard of you in 6 years. Congratulations, you got a transfer. Okay. Number 3. How many variables are we measuring? No. How many variables are we measuring? No. One variable, it's your admission decision. Tricky. One variable, your admission decision. Because even though there's 3 different things that can happen to you, you get in or you don't, right? Okay, so you go to different places, but you either get in or you don't, right? Okay, the people that don't get in are waitlisted or denied, but you're still not in, right? All right, as a class, we're going to write down the hypothesis for a significance test. The null is what? What are we trying to find? Well, we're comparing Michigan and Ohio State, right? So the annul is going to be that there is no difference in distribution of admission between Michigan and the other school. Okay. The alternative, that says boo, boo school. All right. The alternative is that there is a difference in distribution of admission between Michigan and the bad school. I feel like I'm gonna get like a letter from like Ohio State that's gonna be like cease and desist. It's gonna be great. I wish somebody would. All right. What's the acceptance rate for all students in the samples? So how many people got in for all of it? 105 out of how many? Okay, so 105 divided by 350 is 0.3. So 105 divided by 350 is 0.3. You said better than nothing, but like, how many people actually apply to both of those schools? So, like, that's so sad. So find the expected counts, assuming the null hypothesis is true. Okay. I think we're gonna pick up on this tomorrow. Yeah. Yeah. So we'll start on 6 tomorrow. Okay. I need you to do the 12.1 because if you can't do 12.1, you really can't do anything else. So I gave you homework. It's due Friday. It's one sheet. It's one sheet. You can do one sheet. I'm just playing. One. Due Friday.